Okay, can you all see my screen?
Yes.
Okay. First of all, I want to thank Riet for inviting me, and of course also the Dewatering Institute. I will present a project that we are doing in Brussels. I will not repeat the title, it's quite a long one, so Riet already introduced it. So let's go to the agenda straight away. So I will give a short introduction about the company Traqua, the team, fluorescent dye tracing, which we used here as a technique, give you just a little bit of a geological and hydrogeological context, which of course is quite important in this project. Just a general idea about the metro, so underground project that we are working on. A small introduction about artificial ground freezing, and then go straight into the works that we did in this project. So first of all, who are we? We are a small hydrogeology company. We are actually a spin-off from the University of Namur, which is in the south of Belgium. And we are specialized in tracer testing, or also called dye tracing, and hydrogeology, with a focus, of course, on groundwater, but also surface water flows. We analyze, monitor, and characterize groundwater networks, or also surface water networks. And we can do this in different circumstances. We can do this in natural areas, so natural aquifers in rivers and lakes, but we also apply our methodology in artificial systems like distribution or drainage networks and sewer systems, or even in industrial locations such as mines, construction sites, which is the case here, drinking water catchments, etc. To do this tracer testing, which I will explain in a minute, we have developed our own instrument, which is called a stream fluorometer. It's an optical device that is able to detect fluorescent dyes that we inject ourselves into the water system. Since we developed and produced them ourselves, of course, we have many available, which really helps in giving a really in-depth view of the situation. So we can provide really high resolution measurements, putting in place a whole network of these stream fluorometers. This is just quickly an example of the instrument that we used also in the project that I will present today. So it's quite a compact instrument, but I will not go too much into detail about the technical aspects. Feel free to look at it at your own time afterwards. So now about the team. There's Amel and myself, who are the co-founders of Traqua. We started Traqua almost now 4 years ago. So in 1 month, we will celebrate our fourth birthday. It's always a happy moment. And last year, our team doubled because we hired also Morel and Roma, of course, both hydrogeologists themselves with expertise in tracer testing as well. The three of them, me, myself, I'm not a hydrogeologist, I'm the business developer of the company, but the three hydrogeologists have experience in different settings. In quarry sites, we do some geothermal projects as well. They have experience in karst systems. So it's among the three of them, there is quite some experience within the team. Now about dye tracing. So what is this all about? Dye tracing is a methodology to really characterize groundwater flows or surface water flows, but in general, it's used for groundwater. So the general idea is that you will put in place a whole monitoring network. In our case, this is done with our own optical stream fluorometers, but this can be done also by an automatic sampler. This can be done by manual sampling. This can be done by activated carbon packs. So all kinds of methods that will be able to measure or capture or detect a fluorescent dye. Now about the fluorescent dye, this is a dye that we inject ourselves. So it's an artificial dye. It's not present in the natural environment. Of course, it's also not toxic. And when we inject this dye in either a stream or a piezometer, it will distribute within the groundwater, and the measuring network will then be able to detect this, this fluorescent dye. This results in what we call a restitution curve. This is, of course, a textbook restitution curve. It looks very beautiful. In general, it's a little bit more complex. But what we see here, I don't know if you can see my the mouse pointer.
Yes.
Yes, perfect. So what you can see here is a time of arrival of the dye, which gives you an indication, of course, about the speed of the groundwater flow, the velocity. It gives you a maximum peak, and then it goes down again until, of course, no more dye is detected, and it's all passed by the monitoring network. How this peak looks like, whether it's more flattened or very straight, or maybe not many dyes detected, this all gives some indication about connectivities, velocity, residence times. You can detect, you can analyze the hydraulic dispersion, effective porosity. Of course, there's a lot of mathematics and formulas behind it, but this restitution curves can provide you with quite some information. Now let's go a little bit deeper into first of all, the geological context of Belgium, for those who are not familiar with our tiny country. So we are lodged between France and Germany, and even we are very small. The geology is quite interesting. It's very diverse. We have a quite flat, sandy, clayey, silty area in the north, and then we have a very older, very heterogeneous geology more in the south. Brussels, it's located in the northern part, so it's more sand, silt, clayey underground, which, as you can see here, when we zoom in a bit, it's quite complex. So just for later indication, the red dot is where our project is located. So what is the geology of Brussels? First of all, we have a Brabant Massif, we call it a bedrock. On the coupe, like on the cut, we can see this purple layer. This is the bedrock. It's quite deep in the north, but quite shallow. It doesn't come to the surface in Brussels, but it's quite shallow in the south of Brussels. Of course, this is the oldest layer, and it's on top of that, we have all kinds of sediments. As we saw on the earlier map, it's primarily sand, silt, there's some clay layers as well. And also to note here, you can't see the river, but this is the Seine River. It's basically the old riverbed. If we look at the next map, we look a bit more in detail to the hydrogeology. And just for indication, the light blue colors are locations where the groundwater is quite deep. The very dark blue colors are locations where the groundwater is very shallow, so it's very close to the surface. And again, we see our red dot location. As you can see, it's an area where the groundwater is very close to the surface, let's say around 2 to 3 meters to the surface. Again, in the old riverbed of the Seine River. The Seine River doesn't flow freely anymore in Brussels. It's taken up partly by a drainage system and even some sewer system. So it's no longer there visibly, but of course the groundwater layer still is a remnant of this river basin at this location. So now about the project. So we are working as a subcontractor on a project for a new metro line in Brussels. It's called the M3 metro line, and the goal is to connect the north of Brussels to the south of Brussels. There's already a trains. There's already train stations. There's already some tram stations, but none of them are really well connected. So the goal of this new Metro 3 line is to really have a nice connection all the way from the north to the south of Brussels. So really to improve Brussels public transportation, they invested a lot of money in really improving public transport. The whole line will be about 10 kilometers long with 18 stations, metro stations in total. But of course, these are not all new. A lot of them already exist, but will just be connected better with this new metro line. They will also convert some pre-metros or tram, which is usually above ground infrastructure, to this new metro line, and also construct some new tunnels and some new stations. The project is expected to finish by 2032, but as we all know, construction projects usually take a bit more time. But now for this first phase, they only plan to construct one new metro station, which is the Toots Tielemans. For those who know jazz, maybe you know him from the harmonica. He's a very, well, unfortunately he passed away, but he was a very famous harmonica player. So this is the new station that we will be working on, or that we actually already worked on. So the Toots Tielemans, the goal is to make this area, which is called Stalingrad area, a lot more accessible to the people who live there. It will also be connected to a nearby other Lemonnier station. It's a very complex, very big project, especially for Brussels or Belgium norms. It's quite a big project, probably one of the biggest in recent years. And the site is very, very complex. So it's a very urbanized area. There's a lot of shops and buildings. There's a large connecting, how do you say it, like carway or a highway in Brussels. There's a train station nearby. There's already an existing metro line. There's a tram line. There's, of course, the sewers going through the area. And there's also another huge building nearby, which is called the Zuidpaleis or South Palace, which is not the most stable building, but it's quite a renowned building. It used to be a covered market, and now it contains the sports facilities and administrative offices, etc. And there is a procedure in going on to classify this building because they want to keep it. The problem is part of the new metro tunnel is supposed to go underneath this building. So that's another challenge of this particular area. So now if you go a little bit deeper into the construction site, this is a Google image here on the map. You see it's basically the same. So we can divide the construction zone in two big parts. So the blue one is where they will build already part of the tunnel. This is an open, or at least it was an open construction pit. And then we have another small site here. Of course, this is all one big construction site, but they are divided into two parts, and the car highway can continue in between them. Here we can see the entrance of the tram, the already existing tram tunnel, which enters here and turns north and comes out again here. If you go here to the south, following the red arrow, we will arrive at the Midi train station. So there's the train station nearby. There's already an existing metro station Lemonnier here in the north. And if we go a little bit more north here, we have this big famous South Palace that is going to be protected maybe in the near future. This is just the building of the construction site itself. And the challenging part is this light green part. This is why they want to create a new tunnel with, of course, the Toets Tielemans metro station that will, remember, there's already this tramway going this way. So this tunnel for the new metro line will go underneath the existing tramway. And remember what I said before, it's already quite a complex area. There's metros, cars, train, a lot of buildings, and a very low or rather high groundwater level at the same time in a very silt, sand, clayey underground. So you can imagine a little bit the complexity of the site. Here we have just a general overview, very broadly, an overview of the underground. So we have, this is the bedrock. We have some clay, a large clay layer, some sand, another clay layer, which is roughly at sea level, the top of this clay layer. And then we have all kinds of mostly sand, silt layer on top of it, which is of course part of the alluvial deposits as well. So it's very, very heterogeneous layer, and the phreatic layer, very, very shallow on this particular site, 2 to 3 meters beneath the surface. Again, this is a little bit more in detail what the metro tunnel will look like. So this is part of the metro tunnel that is already built. This is, as you could remember, this is the first part of the construction site here. This is the other part of the construction site, and the tunnel will be constructed here. They will use a ground freezing method for this. You could ask yourself why a ground freezing, artificial ground freezing, and why not, for example, a tunnel boring machine? Well, this is exactly the reason. It's a very short bit, but it's well, there is it's not straight, so there's a curve in it, which of course can't be done by a tunnel boring machine at such a short distance. So this is a limiting factor to use a tunnel boring machine. Another limiting factor, of course, is the fact that it would be already underground. It will be underwater. The groundwater level is very high here, and already existing tramway tunnel, which is roughly going this direction, is already in the groundwater layer. So this new metro tunnel would have to go underneath it, which makes it extremely difficult or almost impossible for a tunnel boring machine. So that's why they choose to implement this artificial ground freezing on this specific, particular spot of this metro project. And this is where we come in. So roughly what is artificial ground freezing? Very simply stated, it's freezing the ground with a coolant. Usually this is a nitrogen followed by a brine, to freeze the ground in order to stabilize it. So this is very good methodology in sand and silt, which are of course not very stable. And freezing this ground, and of course the groundwater in this ground, will be able to stabilize this area. It's commonly used for the construction of shafts and tunnels, so which is the case here, and usually in areas where the geology is quite complex and difficult to work with, and where the groundwater levels are high, which is also the case in this project. Here you see a little picture. This is not from the site. Unfortunately, I don't have pictures. Of course, the ground freezing hasn't started yet, but I don't have pictures of the tubes, neither, because I was not allowed into this specific zone of the project. Artificial ground freezing has some advantages. So of course, it can stabilize the ground. It's also very useful to control the groundwater, because it will just freeze the whole area. It can be applied to a whole range of different soil types, and it's really a temporary measure. So if managed correctly and frozen at a good speed and then thawed at a good speed, it will not alter the soil properties. So once the zone is defrosted or thawed, it will go back to the original state. Unfortunately, that has also some limitations. It's very costly because you have to constantly inject a coolant, so either liquid nitrogen or a brine, for several days. Of course, this is very energy consuming. You also really have to carefully monitor the freezing and the thawing. You need big containers to store this coolant, and you have to be able to reach the site with all the trucks and machinery. So it might not be suitable for all sites, just for logistical reasons. And another potential limitation is the groundwater velocity. So if the groundwater velocities are too high, it will not be able to remain frozen, because just the constant flow of the groundwater will defrost the area, which is, of course, a very important factor. And this is basically why we were called into this project, was to do a very local hydrogeological analysis, really to analyze the context to determine how much coolant, how much brine they would have to use to keep this area frozen for the construction of the new metro tunnel. So this might look complex, but it's not that complex. So here on top, we see this is where the tramway goes. So it's of course it's underground. We can see here sideways, or like basically underground, we see the tramway, which is this part. We see one construction site and then the smaller one on the right. And the tunnel will be built underneath the already existing tramway on this part. So of course, the part that they want to freeze is this zone, which is not very large, but it's quite important and also quite complex area. So what we started with is, of course, we wanted to do a first general determination of flow velocities in the zone where the ground and artificial ground freezing would be applied. So this is exactly this area. And we did this by implementing 4 dye tracing tests, or dye tracings. There you can see 4 boreholes, so 2 on this side, 2 on this side. Some areas were not accessible, so we kind of had to choose the borehole locations outside of already existing constructions and infrastructure. And we did our tracer tests under pumping conditions, which I will show you a little bit further. So here again, you see the sideways view with the already existing tramway tunnel, 2 boreholes on one side, 2 boreholes on the other side. This is the top of the clay layer that we saw earlier, with more or less 20 meters of alluvial deposits on top of it. Here you can see that the groundwater level is very high. You see this very thin blue line here. So basically the already existing tunnel is already half immersed in the groundwater. The new metro tunnel, which will be underneath here, will be completely surrounded by groundwater. Okay, so what did we do for the tracer testing? This is the general setup of the tracer test. We so just to clarify a little bit this schematic overview. So we have an injection well and a pumping well on the other side. Here you can see the thickness of the aquifer. Of course, since we are actively pumping, you have a cone of depression here, so the piezometric level will lower a bit near the pumping well. You have the tracer injection, which is going to move to the pumping well at the apparent velocity, you have the effective porosity of the aquifer. This demonstrates the thickness, and then we also had our stream fluorometer that I showed you earlier outside in a detection cell, or a cell that we made ourselves. You can see an example here. So our instrument is set up in a waterproof measuring cell. Water is flowing in and then flowing out again. And of course, like this, the instrument optically detects the passage of fluorescent dye. So here again, on the picture above, you see pumping going into the system, into the measuring cell, and going out. The water was just afterwards rejected into the sewer system. There was no provisions to put it back into the aquifer. The pumping rate was constant. It was kept constant by another company who did the drillings. So that was a good thing, of course, to have a constant pumping rate if you want to do a dye tracer test on the pumping conditions. So we injected a known mass or quantity of tracer into one of the boreholes. It moved to the pumping well, where then we analyzed the restitution curves that we saw earlier. This gives us our apparent velocity, because of course we know the fixed pumping rate, we know when we inject, and we know when the tracer arrives at the probe, which is just outside of the pumping well. This apparent velocity, of course, depends on the effective porosity of the aquifer, the thickness, the pumping rate, and the distance between the two wells, which is also known. And based on this information, we can then analyze the real velocity of the groundwater. Of course, this is only possible in certain conditions. So here we assume radial conversion flow, that this radial conversion flow is valid. There were other pumping tests that we did later where this was not the case, and then you need to do more complex calculations to come up with a range of real velocities. So this is the first dye tracer test that we did between the boreholes that you can see here. The distance was very, very short. This was done on purpose because we just wanted to have an idea that since this was the first tracer test that we did, we just wanted to have a general idea about the effective porosity of the aquifer. Here you can also see the general direction of the groundwater flow. And I'll just switch to the, so this is another tracer test that we did. We did 4 in total. Another one a bit further. You see that the cross ones, they are both going exactly through the zone where the ground freezing will take place. And then a last one, a test for going on from this borehole to the other one. You could ask yourself, like, why didn't we analyze directly in the zone where the ground freezing will take place? Maybe with a single borehole pumping test or others. But of course, in this case, this is not possible because there's already an existing underground tramway tunnel in this location. So there's no way to access this exact location where the ground freezing will take place. So this is a kind of a turnaround methodology to still have a good view on what is happening underneath this zone that is a bit of a black box, but still needs to be quantified since the ground freezing will take place here. So this is the result of the first test. I will only show you this one because the other ones didn't show the radial convergence model well, it wasn't valid in the other locations, so the interpretation of the results is a lot more complex, which might take us a little bit too far, and which is also not my expertise. So I will, if you have questions about the other tests, feel free to contact one of my colleagues. But what we see here is, so remember, this is the first test, the very short distance between the two boreholes. What we see here is the first arrival time of the tracer, which is already around 2 to 3 hours. We see the concentration, maximum concentration, and then the dye disappears again until it's again back to base level. We also had on this first tracer test almost 100% tracer recovery, which wasn't the case on the other tests. So based on the fact that we always had 100% tracer recovery and a very nice restitution curve, in this test we assumed that the radial conversion model was valid, but again, this was not the case for the other tests. But it helped us to calculate an effective porosity of this area. Other characteristics were measured not by ourselves, by other companies. So they did pumping tests for the permeability, and we also monitored the piezometric level in the 4 wells to have a hydrogeological gradient. And of course, the effective porosity that we analyzed from this first tracer tests, where the radial convergent model is valid, or where we can assume that it's valid. So from this first phase, which contained the 4 tracer tests, we already noticed quite some things. First of all, we know that the aquifer was extremely heterogeneous, not from the first tracer test, but we know from the 2 other tracer tests or 3 other tracer tests that aquifer is extremely heterogeneous. The thickness varies, which we saw from borehole and CPT tests. There's a lot of variations in the permeability and the porosity. There were some clay lenses as well. And of course, there's an effect of the already existing tram tunnel as well. The model, so the radiant convergent model, is not applicable for this whole context, although we did use it in the first test just to come up with the effective porosity. But considering the very heterogeneous situation of the underground there, we decided to also permanently monitor the piezometric gradient afterwards, so after the tracer testing, to really see what's going on there while they were constructing the different parts of this new metro tunnel. Anyway, from this first phase, instead of coming up with one real velocity, we came up with a range of real velocity values, since the area is so heterogeneous. Unfortunately, I can't give you the exact results because the project is still ongoing, and we can't just communicate all the details. But the result, I can tell you that the result of this first phase with the tracer test was that we provided our client with a range of real velocities. Unfortunately, the higher velocity or potential velocity was getting closer to what is the limit for ground freezing. So this was something that they really had to take into account for, of course, for the next steps in their project. This was something else that we did. This is even more complex, so I will not show you the restitution curves, but it again demonstrated the extremely high heterogeneity of the underground. So this is another project outside of the 4 initial tracer tests that we did. This is in natural conditions. So we actually installed 10 fluorometers in in two boreholes, and then we injected fluorescent dye in another borehole. And we really saw that on the different levels that the fluorometers were installed, the dye was arriving at vastly different times. So the speed within the aquifer of the groundwater flow is very different depending on the depth. So there's a lot going on here, a lot of heterogeneity. So it's going to be quite tricky to implement the artificial ground freezing here. So once we knew that we had an idea about the real velocities, or at least the range of real velocities, we decided to continue with a continuous water level monitoring while they were doing the groundworks. So they were already building other parts of the tunnel before and after this tricky location where they will implement the ground freezing. And this to have a general idea about, first of all, variations due to natural conditions. As you can see, there's a lot of pictures of me and my colleague because we mostly did the monitoring for the whole year. And of course, there will be variations due to the groundworks. So the tunnel before and after the tricky part, let's say. So we did monitoring for 1 year. And this is the picture that you saw earlier, but what we saw was already quite an influence on this first part of the metro tunnel that was built during the year 2023. What they did actually was building a big wall straight into the underground for this first part of the metro tunnel, and this wall effectively blocked part of the groundwater flow, which is going in this general direction, and you see that it already has quite an effect. So this was quite a visible effect of the groundworks that were going on in this area. And you can also see the level of the let's say the groundwater level. So you have quite a large hydrogeological gradient. And what is happening actually, since they are building a wall here for this first part of the metro tunnel and another one on this side, what will happen is they will force all the groundwater that is flowing from south to north through this still open place, because this is where they will ground freeze. All the water is actually pushed through this small opening, which of course even increases the groundwater flow. It was already quite high and makes it even more challenging to implement this ground freezing. Because of course, remember, you need, if the groundwater flow is too high, this will make it very challenging to keep the ground frozen. So that brings us to the next phase, which started now. We didn't do any monitoring for a whole year because they stopped working on this side and continued working on the South Palace site, a little bit further up north. But what we will start doing now this year is again do a continuous water level monitoring. We use this little divers to do this. I don't know if you're familiar with it, but you can just drop them into the piezometer at a certain level, and they will automatically monitor basically the pressure, and based on the pressure, it will give an idea about groundwater level fluctuations. So again, the idea for this year is to monitor the water level again for a whole year, while the project coordinators will start pumping on the southern side of this wall that they built to reduce the hydrogeological gradient and to stabilize this groundwater level. So what they will do is, you have this already existing wall here of one part of the tunnel. There's some infrastructure on this side. water is still flowing freely underneath the existing tramway with quite a high hydrogeological gradient because, of course, all the groundwater is forced through this zone. And they will start pumping on this southern side to try to lower the hydrogeological gradient and as such also lower the groundwater speed so they can safely implement this ground freezing method. So that's going to be a project for this year. I hope everything works out as they want. It's quite exciting. And that is what we contributed so far to the project. So thank you.
Sure. Excellent. Thanks, Sophie. Yeah, quite complex project there you got.
Yeah, very, very, very much.
Sounds exciting. I don't know if there's any questions. You can either type